Welcome to this session, Big Data with Python, which you find in the third day. That's the fourth lesson. So we will cover big data, and we start to speak some words about high-performance data analytics. And what is this? Well, it's a subset of high-performance computing where the focus is not the computing or computing power, but more on the data size, large data. The data could be output from computer models and simulations or from experiments and observations. So you want to pre-process or analyze or visualize these results. And for instance, it could be also in machine learning. So big data refers here to data sets that are too large or complex to be dealt with by traditional data processing application software. So the challenges here is about capturing data, about storage, how to analyze this, search, sharing, transfer, and so on, visualization as well. Yes. And maybe you work with big data already, or this is completely new for you. So you might remember this one from the pandas lecture. So we see here we can use pandas in many cases, but sometimes if the data is more image-like, maybe one could try X-array, which is another package. Also, if you have more than 3 gigabytes needed in memory, or a bit more maybe, depending on your system, how much memory you have per core, then Dask or polars might be the solution for you. So the constraints here is, on one hand, the storage of big files or big data. So we speak a bit about where to store the data, or I mean, in what format. Is it effective the way it is stored today? Maybe there are other solutions. And the memory. So the difference between storage and memory. Storage is what is on the hard drives, and which is there also when the computer is off. So it's basically the files. The memory, on the other hand, is what is loaded for your program. So if you read a file, for instance, by a program, it is loaded to the memory. So the information from the file is available for the program. So we need to cover storage, as I said, reading into memory. Maybe there are ways to just read parts of the files into the memory. We will, and also chunking, that is divide the data into chunks when doing calculations. And one maybe obvious way is to basically allocate more memory. And let's look at this. This is maybe the preferred method if you are already running things. You may have tools from a colleague, or you have developed something yourself. So if you don't want to or cannot update the code, or use other packages, then this is an easy solution, because then you can run the program as usual, but you have more memory to play with. Yeah, so that you can deal with larger files or deal with larger data inside the memory. Yes, file format, choosing the right format for reading and writing. Also choose the right Python package, could be one thing. And chunking, yes. But now back to allocating RAM. So how much is actually loaded into the working memory? So that is one thing to just notice. Maybe you have seen this out of memory error, meaning that the memory is not enough for your tasks. Yes. So this might happen, and then you can think of maybe change the problem as well. You may also think about if you create variables in your program that are just intermediate steps, so maybe you can erase them after some time, so that you clear parts of the memory that you're not needing anymore. Yes. Yeah. So what to do? You can allocate many cores on a node that will give you more available memory. And also if a basic node, maybe it's 128 or 256 or 384 or something. If that is not enough for your program, then there are on most of the centers fat nodes with at least 512 gigabytes, up to 3 terabytes on one of the classes, if I remember correctly. So one thing, you can allocate many cores because that automatically will increase the size of the memory. On some classes, you do not have to request additional CPUs cores. Instead, one can use the slurm options --mem or --mem per CPU. One of these. You should combine these because that doesn't make sense. So you do not have to explicitly run threads or other parallelisms here. So allocating 7 nodes for one big problem. Yes, also I should say that you can't allocate 7 nodes because the memory cannot be shared between the nodes. But as you will see later, you could ask for 7 nodes if you are using like Dusk. Then it's possible. Because then you distribute the work in another way. You don't need the shared memory in some sense. Yes, so shared memory is one key thing here. That is a memory that is shared by different threads, but this works only within a node. So the principles here to allocate more nodes or more memory is to think, to ask for more cores and to get what we want, you first find out how many gigabytes per core we have. So if you know from your cluster that one node is 128 gigabytes and it has 20 cores, it will by default give you 6.4 gigabytes per core. Maybe a little bit less because of some overhead or system tools running in the background. So about this amount, and if you if you want like 32 gigabytes, then you see that this will perfectly scale with exactly 5 here. But it could be good to take a little bit more to be sure. If you use the mem clause, you do it like this, dash mem, and then the number, and then G for gigabyte, T for terabyte even. Kilobytes, I don't think that's very useful in this case, and not the M either. Or you have the memory per core way to say, so, okay, I need 16 gigabyte per core, then it will scale up. So if you ask for 5 CPUs or cores, you will get 80 gigabytes. Okay. The fat nodes, typically you can only allocate a full node here. You cannot book a part of the fat node. You can only allocate the full one. And here you may have to add a dash P for partition, and then depending on your cluster, yeah, see what arguments you need or options to get this fat node. Yes. So if you are running this dash mem, it will be the memory part of the node that you will have to pay in terms of core hours. So the core hours stored from the project may be set to the maximum of number of cores that you allocate and or the memory part of the node. So I mean, if you book memory that equals maybe 6 cores, then you will be then you have to pay the number of cores, 6 in this case, 6 times the hours. So there is no win to ask for 1 core but much memory. Then you have to pay for the memory instead, basically. Yes. So you can pause this session, this video, and try out this exercise. It is both about understanding how you come to some conclusions, and also start an interactive session here, which we will use at a later date. Yes. Documentation links. We also have the table of hardware here. Yes. Yes. So I will continue a bit with the file formats. And I guess you are already acquainted with the bits and bytes, the smallest parts, what do you say? Smallest building blocks of storage and memory. You may have numerical data or text data, and you may find out, the different data types. You may recognize these. There are also some other ones that could be helpful in some cases. But I don't have a link here, so you might Google this. I know there will be some information about data types also in the last session about machine learning, day 4. Yes. But now the format of the data. So is it in some kind of table format, maybe? Or gridded, like physically grid? It could be an atmospheric model, like a weather climate model, where you have the 3D of the atmosphere. It could be anything. So we're in modeling here. Metadata is one thing to think about. That is the data describing the data. You can read more here if you're interested. CSV, comma-separated values. I think that's very, very common. We also have HDF5, which is a kind of hierarchical data format, where we involve metadata inside the same file. So when you read this, you can ask for the metadata, and then it will give you that information. I mean, you can, yes, maybe it's better. Yes, so it could be multiple data sets also in a single file. So typically multi-dimensional arrays. And so you see also for all these, if it's in binary format or in, let's see here. Yes, tabular data. No, let's see here. Text format, for instance, for CSV. But here's binary, so it's not human readable, but it is more effective in the storage. You can also see the base use cases for different data sets here, and also the packages needed to read the data. NetCDF, I can also briefly mention, it's based on HDF5, but it has a standardized structure of datasets and metadata related to these datasets. Yes. And here's an overview where it's suitable or not. Yes, so we may see also, okay, it's not here. We can see that, yeah, well, the crosses here would be binary data, whereas this is text, so you can read it, CSV, JSON, and Excel, for instance. But when it's human readable, most often it's not very effective. Also, we see that for storage and sharing, we see that Excel is not a good way to do this. But like this HDF5 and CDF is very good, and JSON as well, and also CSV, because it's a standard that everyone can easily use. Yeah. An exercise here is about, for one instance, about reading the CDF, and this I want you to answer. What about using the CDF files in the memory? So, what can you say about this? And then view file formats. So to see if some are more relevant for your work, and also would you look at other file formats and why compared to what you use today? And then it's also an optional exercise. And trying out this exercise by reading an .cdf file. Yes, so if you scroll down a bit, one can play a little in .cdf and learn a bit about that. So you can pause now, or you continue directly, and we look at computing efficiency with Python. So you might know that Python is an interpreted language, and you have many features that make development rapid, but the price is reduced performance in many cases. So, I mean, it's easy to to develop and then run directly. So you have the Python interpreter that in real time, more or less, transform your Python language to machine language. And also you have dynamic typing and flexible data structures. So that means that the interpreter has to understand and give the correct instructions to the machine, and that takes extra time. So yes, you don't have to compile after every changes, but on the other hand, you lose performance. But for rapid development, it might be faster anyway, because you don't have to wait for the compilation. Yeah. Okay. But there are some packages that are more efficient than Number and Pandas, and that's because they have backend routines that are written in Fortran or C. And for instance, we have in SciPy some of these functions. Also, if you are more interested in this, you can check this ENCCS course material. And if you don't know it, ENCCS is the Swedish part of the EuroCC National Competence Center. Yes, so that is about Python and also SciPy. Then we have also Xarray package, which is a package that builds on NumPy but adds labels to multi-dimensional arrays. So it looks like and are intuitive like NumPy, but more intuitive, I could say, because you have you have the coordinates and attributes, so you can ask for one axis of the coordinates, for instance, and get the information from there, instead of trying to understand what the different indices mean in the matrices that you get. So with the labels, it's easier to get more concise and less error prone. Also borrows from pandas, and it integrates tightly with Dask for parallel computing, which we'll mention in a while, and also particularly tailored to working with NetCDF files, but also other files as well. And there is an exercise below where you can test this out a little bit. Another very useful package is the Dask, which we had here. So if you trespass the memory, this is the solution. So it consists of two parts. One is Dask clusters, which is a scheduler for computation. So similar to other workflow management systems. But we don't cover it here. If you're interested, you can go to this ENCCS course. What we will cover here is the big data collection, like parallel arrays, data frames, lists. where you can distribute when you can look at the data that is larger than the memory, actually. If you want to dig deeper, there is also a link to same course, but another session. So it has parallel NumPy arrays, pandas data frames as well, and Python lists. So basically, this is a parallel version of NumPy and also for pandas, so on, which is very nice. We will see more about this in a little while. I can mention also that we have there are packages for machine learning and also distributed, which is a lightweight library for distributed computing in Python. And a little bit about distributed, you will be covering tomorrow with Pedro, or the lesson 4, parallel computing with Python, this one. Yes. Okay. This was what is not included here, but we come back now to the desk arrays. These ones. So we focus a little bit on that. So desk array uses so-called lazy execution. This first build up. Yeah, so you define first what to be done, and then Dask builds up a complex large calculation symbolically. So it's there symbolically. So so that's the definition. And then you may do several steps, and then with your last step, Dask understands that, okay, now it's time to make the calculations according to the information I've got so far. So then it is scheduled for execution, and it could be in chunks like this. But the important thing here is that things are piped. So you get some information and calculations done in a workflow way, more or less. Yeah, a little bit more about this. Here we see here. Yes. So chunks. Thus divides arrays into many small pieces, as small as necessary to fit into memory. And then we have this laser computing. So that means tasks are queued and no computation is performed until you actually ask values to be computed. For instance, print the mean value. So first we have a definition. The data is loaded into memory and computation proceeds into this streaming fashion or pipeline, block by block. And then in the end, the data is gathered. Chunking can happen automatically, but you can also define the chunks yourself like this. And note here that the number of chunks does not need to be equal to the number of cores. So you could have booked one core and still you can use the chunking processing. You could also book several number of cores, and then there will be some parallelism here. So parallel workers and then results combined. But you can still have less number of cores than the number of chunks. What shouldn't be used, I guess, is to book more cores than the chunks. So chunks should be equal or larger. Otherwise, you are not efficient enough. I mean, then you're allocating cores that you are not needing, that you don't need. Yeah. Yes. Yeah, so if you have multiple cores, the chunking and the calculations on the chunks can be done parallel, and then that means it will be much faster. Yes, and also you can distribute to other nodes. So you could book here actually 7 nodes. You don't have to think about this shared memory. Instead, it's distributed, and the different processes does not need to know anything about the other processes. Yes. It could look like this. So basically, this line is the instruction, the definition. So it builds up what to do. But here, yes, and then this is defined here, what to do as well. But yeah, this is interesting. Should it be an equal sign somewhere? Yeah. Yeah, I just think this should be a plus, an equal sign. Yes. So when you want the information, I think you can write the print, and then it actually do the calculations. I should be sure about this. So let's look. Sorry. We have the example here. Yes. So in this case, we have the definitions first, and then we have the compute. So we can compute by this compute function on y. So here nothing is done, but here we start the process of doing all these calculations. Yeah. So I could add here that many things are happening in behind. So thus we'll understand how we do this most efficiently. Yes. The third last package I want to briefly cover, that is polars. It presents itself as a blazingly fast data frame library. So yeah, you see it's related to pandas a bit. And it can use several cores. And also handles data sets larger than the available RAM. And some other things. You can also read more here. You have the link here, and I can also mention that it can use NVIDIA GPUs. Parallelisms written in Rust, so that's why it's very fast. Yes, support for many different common data storage. Yes. So the exercises here is first to set up the environment. In the previous exercise, you logged into ThinLink or on some kind of web on demand. And you also asked for 6 cores, I guess. The next step is to load the different bundles if needed on Pelle and NSC, I think. Yes. Yes. Well, one can do a pip install and Pelle. Yes. You load these ones precisely. Yeah. Yes. So the first exercise then, when this is up, the software modules are loaded. You have started Jupyter. I think Jupyter is the best. You could try with the Spider, but I do not have any instruction for that here. But it should work. For Spider, you will use, at least for Pelle and Tetralit, maybe Dadel. You have these conda environments that was created the second day. Yeah, okay. So first exercise is comparing NumPy and Dask. Oh, sorry. And yeah, see the performance improvement by using Dask. There is any, and maybe change some numbers here. And I forgot to update. No, oh, okay, it's correct. 20,000 here, and NumPy 20,000. Yes, so that's okay. So that's the first step to just see the difference. Then you can play a little bit by the chunk size, and maybe also how big this one is, and to see what happens with the performance when we change the chunk sizes. Yes, and we have some answers here. If you want to, you can look into Xarray. Here we have just a note or a discussion about when to use Xarray over NumPy. And also here we have okay, interesting. Yeah, it seems it was not, if I do like this, Control C. Yeah, here it is. So I will change this in the material. Here you can try, you can also choose the version that you have installed to the one you're interested in. You see it here in the lower right corner. You can view what is here, like user guides gallery, for instance, we can look at. And try something that seems a bit relevant for you. Yes, you have some links here. And also we have, yes, about the same for pollers, where you can browse the documentation. Here, and going down, we have one example here directly, and then we can go also here and find specific things. Even getting started might be interesting for you. Yes. So a summary here. Think about this. Maybe this is relevant for you, and then I encourage you to actually dig deeper and learn more. And I just saw some links to courses out there that you can join. They also have the material, the online material, which you can cover in your own pace, of course. So, key points: allocate more RAM, choose a file format suitable for your problem. One can also, I didn't cover this, store temporary data in a local scratch. That is the hard drive that is located on the compute node where you're working. In other case, you have your storage on a big storage server, and there might be some latency if you have a lot of input to output. I mean, reading and writing of a file. If you do this very much, maybe even every second, then it's much, much better to have the big file moved to your local scratch, which is on the compute node. And this is called this when you start a work on a compute node, either via batch, or interactively, there should be this environmental variable, which give you information for the path. So in the beginning of a batch file, you can do a copy of of the file you want to work with to this variable. Yes. Packages, we covered a bit X-array and Dusk, and to some extent polars as well. Yes. And here we also have, you have different courses here. And sorry for this. So what here, some guys did a comparison between the pandas, Dusk, and polars, and they also describe how they did it, what computer they use, and so on. And to the conclusions, they say that you should use pandas if you work together with other people using pandas. Because, if the compatibility with other people is important, then this might be the only choice for you. Polars, when performance is critical, a dataset fits in memory. I said before that it uses chunking. I mean that you can use datasets that are bigger than the memory, the RAM. But it seems that the Dusk is performing better compared to polars when this is the case. And especially when distributed computing is needed. And that would mean that if the problem is bigger than one node and you have to allocate 7 nodes, then this will work much better. Yes. So with these words, good luck with your future work and the exercises. Yes. And see you another time.